Okay, so what we'll do here is pretty much discuss what we can expect from a real op-amp. In fact, your next lab, you'll be wiring up a real op-amp. So this part is on a real. Okay, now what you can do is you can Google search for LM741 specs sheet. Okay, the LM741 is one of the many op-amps you can buy, and that will throw up a file which will tell you what are the things like supply voltage, pinout diagrams, and so on. There's a lot of information, like 17 pages. I just distilled some things in this particular lecture. So first, let's talk about the pinouts. And I've covered this, so this will be sort of a review. Pinouts for LM741. Yeah, I just plucked it from their spec sheet. It's basically an IC with 8 legs, and those legs are numbered here from 1 through 8. The way you identify number 1 is by looking at this sort of a semicircle here. Okay, hold it such that the semicircle is on top. The left one is pin 1, and then you go 1 to 4, and then back from 5 to 8. NC means not connected. The ones which we are really interested in this so far in this course is the output, the inputs. Okay, when we say inverting, it means the negative. When it's non-inverting, it means the positive. So typically, I've written this in the so far as V minus. This is V plus. And this is V out. And then the things which we don't really draw in any of those diagrams I showed in class was this V plus and V minus. These are the supply voltages. Okay. I'll come to that in a bit. But the supply voltage is something which you need to do in order to get the op-amp to work, because an op-amp is no longer a passive circuit like a resistor, capacitor, inductor. It needs power in order to function, and that's what you'll have to do. You'll have to connect this to a power supply. This would be other than what your inputs would be. This offset null we rarely use, but they are used to change the input, for example, might be offset by, say, 0.3 volts, 0.2 volts. So you can get it back to 0 volts by using the offset null. You don't have to worry too much about that. So if you look at the spec sheet, this gives you the recommended operating conditions. This is 6.3 in that spec sheet, which I got by Google searching for LM741. Okay, so there is the temperature, which we don't really bother too much unless we're working in conditions where the temperature won't be what they've noted here. But what we want here is the supply voltage. Now, this is 3 op-amps, 741, 741A, 741C. We're interested in 741. So you want to look at the top line. So this tells you what's the minimum supply voltage, what's the maximum, and what's the nominal. So you should ideally shoot for the nominal voltage of 15 volts. So what you will do is when you do the lab next week, you would connect V plus and V minus, my bad. Yeah, that's right. V plus and V superscript plus, this one, and V superscript minus to plus 15 volts and minus 15 volts respectively. Okay, without that, the op-amp will not work. So let's look how to do that. I just draw a circuit diagram how to do that for the non-inverting, the inverting circuit. So we drew this op-amp earlier in this configuration, negative, positive. P in and P, the non-inverting is connected to the ground. We have a resistor, which then connects to the output. So this was RF, this was R. So this was the inverting amplifier where the voltage gain, the V out divided by V in was, I think, the negative of RF divided by R. Okay, so this is what I've shown so far. Now, as I said, this will not really work in the lab because you've not really connected the supply voltages V minus V plus. So let's draw those here. Stick out. Okay, so let's call this, let's just do it in blue. So let's say that this is the V plus. Okay, I just drew that way, but you take the leg which has the V plus. What you want to do is take this and connect it to a power supply. And since it's positive, you want to connect it to the positive of the power supply, like I've shown here. Okay, then we have the negative. So let's call this V minus. You'll take this and connect it to the negative of the power supply, or you don't really have the notation. So I'll draw it like this, and I'll say 15 volts and say positive is here. Okay, so literally a DC source has a positive, negative. You just connect it to the negative of the DC source. Okay, so you can see that for a circuit like this, you will have 3 power supplies, 1 for V in, 2 for the V supply, and that's about it. Okay, just ensure one thing which I probably should have mentioned is you want to ensure that there's a common ground, which means that you want to physically connect this, and this together. They should have the same ground. Otherwise, what people see is they see that mysterious voltages appear at the output or wherever you're measuring, and that's because you don't have a common ground. So ensure that you have a common ground. Everything is wired up together with a single wire. Okay, this is easier done if you build this using a breadboard. That way, all the wiring is manageable instead of trying to connect it with loose wires. Okay, so now, as I said, this circuit has a voltage gain, or V out divided by V in, as minus RF divided by R. We've derived this in the past. Now let's say that we choose RF and R such that RF divided by R is, let's say, 100, right? Just choose one to be 100 times the other one. Then what we see is V out divided by V in is minus 100. Okay? So what this equation is saying is that if V in is 1 volt, it's saying that V out is minus 100 times 1, which is minus 100 volts. Okay? Now, the question is, would you really see 100 volts across the output? And the answer is no, you will not see 100 volts because there's no power source connected to the op-amp, which is 100 volts. What you see is that, so this is just theoretical. So in reality, you'll see V out will be equal to minus 15 plus 1.4 or minus 13.6. You will see a voltage which is very close to the supply voltage, but it'll be a little less because there is a voltage drop across the circuit. Okay, so you'll see 13.6, minus 13.6. So in other words, V out saturates to plus 13.6 or minus 13.6. You will never see output voltage which is greater than the supply voltage. Okay. Some other things. Here's another part from the spec sheet, the max rating. Okay, so what are we looking here is the maximum. Okay, so this is something which we've already seen. It can be 22 volts for the LM741. The power dissipation is 500 milliwatt, 0.5 watt, which is, I think, it's kind of substantial for an electrical circuit. If you're losing 0.5, it may not be big for, for say a system which is connected to the household supply, which is constantly drawing current and can support itself. But if you are trying to deploy it in the field where you are going to use a battery, then it's just continuously going to be draining 0.5 watts, which is, I think, not ideal. What else? The input voltage. This is something which you need to be careful about. I should write it down. V in max should be minus 15 volts, plus or minus 15 volts. So when you're doing this in the lab, do not connect an input greater than 15 volts. You'll fry the circuit. Yes, that's something to remember. So you want to keep this in mind when you are wiring up the op amp. Okay, let's look at some more things from the spec sheet. Okay, here is a sheet which shows the electrical characteristics of LM741. We'll tackle some of them in today. So let's see. We'll look at the slew rate. Okay, that's one. We'll look at the signal voltage gain, and then we'll look at the input. What else? Nanoamps. Yeah, we look at the output circuit current. Okay, we look at those three. Okay, so let's look at slew rate first. Yes, slew rate, what it is written as volts per microsecond, and it has a value of 0.5. Okay, so let's talk about that and then see what it means. Yes, slew rate. Okay, so for LM741, we just saw that slew rate, which is denoted as SR, is 0.5 volts per microsecond. Okay, it is defined as, it is the rate at which the output voltage increases as a function of time. Okay, so SR is the rate of change of voltage as a function of time, so rate of change of time. And so what does this really mean? Well, if you have an input, say that my input is something like this. This is time, this is my input, and I'm going to plot the output. So this is some circuit, inverting, non-inverting, but this is the input for that circuit. Okay, now ideally what you would expect is that the output, which is V out, is going to be amplified. It could be inverted too, depending on the amplifier, but you will see it more or less looks like that square wave there. However, it turns out that it's actually going to be something like this. So it's a ramp, stabilizes, and then it again shoots down, something like this. So this slope is the slew rate. So the output doesn't follow the input, but it takes its time to go up. So you can see that this is probably very important. If the signal is constant, the input is constant, then everything is fine. It will take its time, settle down to a steady state value, and you're all good. But if you have an input which is sinusoidal, then you will see that those ups and downs will affect you. So an example would be, so this is SR is problematic with an input which is frequency dependent. Okay, so example, sine wave. Okay, here is a sine wave. Okay, and let's look at this is time, this is V in. Let's look at the output. What you see is actually the output will not be like a sinusoid. It will actually be triangular. So something like this. So what's happening is it's actually the slew rate is making it go this way, but before it can settle, you see that the sine wave dips down, which means that it has to decay, but doesn't decay immediately. It has to decay with time, like what slew rate tells you to. And so the output is something like that, and that could be a problematic when you're doing any circuit design, right? You don't expect the sine wave to show up as a distorted sine wave with a triangular output. So slew rate is clearly important, and you can actually fix this. You can fix this by choosing the right op amp, or just choosing the input frequency which will not get clipped. Okay, so how to avoid this? So how to avoid clipping in the frequency response. Okay, so what you do is for a sine wave, so this is only for a sine wave. There are other formulas for other types of inputs. SR for sine wave. So this is a recommendation. What you do is you choose your op amp such that SR is 2 pi f times V, where f is the maximum signal frequency, and V is the maximum peak voltage in volts, and this is in hertz. Okay, so either you choose the op amp which has the right SR, or you choose the frequency based on the SR given in your spec sheet. Okay, so an example. So compute the desired slew rate for an amplifier to handle a peak voltage of 10 volts at a frequency of 15 kilohertz. So for that, SR equals 2 pi F times V. F in this case should be in hertz, so I need to convert that to hertz. So I multiply by 1,000 to convert kilohertz to hertz. And then the peak voltage is 10. And so SR comes out to be 942 times 10 raised to 3 voltage per second, or you can write it in terms of microsecond like it is in the spec sheet. So it'd be 0.94 volts per microsecond. Okay, so our current op-amp is 0.5, and then clearly what you want is the lower the SR, lower is the delta V. And so you probably want as low as possible for the slew rate, right? So SR is an aside. So SR is delta V by delta T. So as this gets more and more vertical, you see that SR, well, SR I think should go to infinity. Is that true? Delta T goes to 0, right? So delta T should go, for this one, delta T is close to 0. So this should go to infinity. So the bigger the value of SR, the better it is. So so we have 0.94, and our op-amp 741 is 0.5, which means that this will not be good. The SR 0.5 will not work for us. We need an SR of at least 0.94. The bigger the value, the better it is. Okay, let's see. Okay, let's go to the next part. Okay, so this is another item from the spec sheet. It's a plot of the gain to the frequency. Now, everything we've looked so far said that the gain is the output, the input is what we compute, right? The V out to V in is AV in open loop, and AV is typically of the order of 10⁵ or 10⁶. It has a very high voltage gain. So this is the gain. Now, when you close the loop, you get, for example, RF divided by R. This is closed loop inverting amplifier. So you can clearly see that here you can choose what the voltage gain should be by choosing RF and R. Typically, people go for 100 or 10 or whatever they want. So V out divided by V in follows this plot at the frequency domain. So as the frequency changes, then this is the plot you get. So if you look at here, you can see that the gain is something like of the order of 10 raised to 5. This is the open loop gain. And then you see that immediately approximately around, it's a log plot. So it's about, I guess, 8 or 9. It rolls down quickly. It starts decreasing very quickly. So higher the frequency, the lower is the gain. And lower the gain, the better it is, because now what will happen is you will not get the amplification need. So on the plot on the left side is the gain in as a ratio. Here it's actually the log. So I think this is 20 log 10 V out P out divided by V in. You've seen this when we talked about body plots. So for example, if you want to see 10, log 10 of 10 is, well, it's so this 20 would come from 20 log 10, 10, right? This is 10. So log 10 to the base 10 is 1. This is 20. And then you just keep going. That's it. So that's the equivalent in decibels. So I will need to define something called a gain bandwidth product. Okay, and this is our fourth term. This is basically this is the ratio of open loop gain to the bandwidth at that gain. So it's a plot, so to say, it's a plot of the gain to the bandwidth, and that GPB is shown in this plot. This is GBP, shows how the gain changes as a function of frequency. Okay, so now let's see how to relate this with the spec sheet. Where exactly is the gain bandwidth product? Okay, so let's go back to this part. Okay, so it's not quite written as GPV, because GPV is basically that particular plot. It's the voltage gain, which is V out divided by V in. And then you say large signal voltage, it's the open loop one. And here is the value. It is 200 volt per millivolt. These values are the minimum values, but we can assume for LM741, it's 200 volt divided by millivolts. Okay, so let's write that down. So from spec sheet, GBP equals 200 volt divided by millivolts. So it's ratio of volt to volt. So let's just convert it so that we just get rid of the milli. So that would be 10 raised to negative 3 volts. So it is 2 raised to 10 raised to 4, 5, I think. 5 volt per volt. So it's a ratio. So it's that big. It's pretty large. Now, for inverting amplifier, we have P out divided by V in is minus RF divided by R. This is something which we've derived and I wrote it down earlier. It's about, let's say that we choose the resistor such that this gain is 100. Okay. So on one hand, we have an open loop gain of 0.2 million, and then the other side we have a closed loop gain of 100. So open loop, closed loop. Okay, so let's look at this on this figure. So here's the open loop gain. That gain is good enough only up to about 8 or 9. But then we have a gain of, let's say, 100, right? Which is here. 100 is there. This is our gain because we chose that particular resistor values. So what this is saying is that the open loop gain is valid for this particular range of frequency, 0 to, I don't know, about 8 hertz. But then if you want to look at this frequency, the frequency at which this gain is valid, so it's valid up to 10 raised to 4 hertz. So you can get a gain of 100 up to 10 raised to 4 hertz. In other words, the bandwidth for this particular inverting amplifier, for the particular amplifier gain is 0 to 10 raised to 4 hertz. In other words, it's 0 to 10 kilohertz. So for that bigger range, you can get an amplification of 100, which is nice thing because that extends the range over which you can use the op-amp, right? But if you want a gain of 0.2 million, it's only valid for that small range, 0 to 8 hertz. And many times our inputs are of higher frequency. So you probably want to factor that in when you're thinking about frequency response. You want to be mindful about how you choose RFR so that you can get the right amplification, because the whole purpose of using an op-amp is to amplify the input. Okay, one last thing and we'll stop. And this is the bias current. We'll see how to use that. Okay, let's look at the output bias current, and then I'll show you how it is used. Sorry, output short circuit current. Okay, so output short circuit current from the spec sheet is 25 milliamps. Okay, what does that mean? Output short circuit current. So this is basically the maximum current across the output should be 25 milliamps. Okay, what this is saying is that if you wire up the op-amp such that the output current is greater than 25 milliamps, you'll blow the op-amp. So you want to be mindful about this specification when you wire up the op-amp. Let me give you an example of how you will factor this 25 milliamps when you build a inverting input circuit. So here is an example on how to use this spec. So let's consider inverting amplifier. Let's say that the input voltage is 5 volts. Call this RF or P out. Okay, so the question is compute the values of RFR such that voltage gain is -2 and the output short circuit current is 25 milliamps. That's a constraint you have. You need to design so that the output current doesn't exceed 25 milliamps. Okay, so let's see how to solve this. So we know that, so we've derived that V out divided by V in is minus RF divided by R equals -2, which means that we know that we need to choose this resistor since that RF is twice R. Now, the question is, what value would you choose for R and RF? Okay, this is still missing one equation. So that equation will actually come from this spec that the output short circuit can only be 25 milliamps. Let's see how to use that. So let me just redraw the circuit. Okay, let me assume the current. So let's assume that this is the current, and then it flows here, but we know the current flowing through the legs of the input, non-inverting and inverting inputs of the op-amp is 0. So the same current will flow here. And we know that clearly from this analysis of this point that I out is I in. So we'll just simplify our life by doing that. Let's call that C. And then what we know is that I out max is 25 milliamps. Okay, so let's see if we can use this information in order to choose RF and R. So we know that this is connected to a 5 volt power supply. So 5 volt or 5 minus voltage at C should be equal to the potential drop across the resistor R. So I in times R, but I in is same as I out times R. Okay, so we need to still figure out what VC is, but we know that VC is connected to the negative supply, so V negative, but V negative is V positive based on the op-amp assumption, but V positive is connected to the ground, so VC is 0. Okay, so we have I out equals 5, or rather, R equals 5 divided by I out. Let's use the maximum value because the maximum I out will give you the minimum R, right? Because of the inverse relationship. So 5 divided by 25 milliamps. So that comes out to be 1/5. It's 1000 divided by 5, so it's be 200. So this is saying that R should be at least 200. This is the minimum value. Because remember, if you make it any bigger, then the current will drop down. It will be less than what you assumed. And then RF is 2 times R, so it's be 400 ohms. That will be the minimum. So that's the answer. That's how you use the spec sheet to figure out what resistors to use.